For our second example, let's find the surface area of the paraboloid z equals 4 minus x squared minus y squared lying above the plane z equals 1. Here's a rough sketch of what we're looking at. The paraboloid z equals 4 minus x squared minus y squared is turned downward and moved 4 units up above the xy plane. And z equals 1 is a plane parallel to the xy plane. So I want the surface area of the piece of the paraboloid which is above the plane. So that's going to be this part up here. So once again, we're going to be breaking the problem into about 3 steps. The first step will be to parameterize the paraboloid and possibly figure out what the bounds are going to be. The second step is going to be to calculate the surface area element, big DS, and then we'll carry out the integral. The integral is going to be a little bit more involved than last time. So first of all, let's parameterize. Now it's important to notice that we're parameterizing the paraboloid, not the plane. Since the paraboloid does have symmetry about the z-axis, it's going to be to our advantage to adapt cylindrical coordinates. So first of all, let's remind ourselves of what cylindrical coordinates look like. X equals r cosine theta, y equals r sine theta, and z equals z. That's not our parameterization. There are too many variables. But we're going to substitute the parameterization into the equation for the paraboloid. So we'll have z equals 4 minus r squared cosine squared theta minus r squared sine squared theta, which is the same as 4 minus r squared times cosine squared theta plus sine squared theta. But since cosine squared theta plus sine squared theta is 1, this is the same as z equals 4 minus r squared. So we take that, substitute it back over here, and we get our parameterization. X is r cosine theta, y is r sine theta, and z is equal to 4 minus r squared. In other words, phi of r and theta is r cosine theta, r sine theta, and 4 minus r squared. Now let's think about our bounds a little bit. Notice what's bounding this cap on the paraboloid is this plane z equals 1. So let's figure out where the plane and the paraboloid intersect. So the equation for the paraboloid is 4 minus r squared, and the equation for the plane is z equals 1. So to find where they intersect, I'll substitute z equals 1 into the equation for the paraboloid. That will give me 1 equals 4 minus r squared. I can move the r squared to the left and move the 1 to the right, which gives me r squared equals 3. So that means that r is the square root of 3. So this circle of intersection right here is the same as r equals the square root of 3 in the plane z equals 1. So the two intersect when the radius is the square root of 3. So when I set up the bounds, I'll be letting r go from 0 to the square root of 3. That's as far away from the z-axis as I need to go. And since I want the entire paraboloid around the z-axis, I'll be letting theta go from 0 to 2 pi. So later on when I set up my integral, r goes from 0 to root 3, theta goes from 0 to 2 pi. So that's the end of step 1. Next, let's see if we can calculate the surface area element. I'm going to try to erase everything except for the parameterization and the bounds. So let's leave that handy. Now this time my parameters are r and theta, so my formula for ds is going to be the magnitude of d phi dr crossed with d phi d theta times dr d theta. So let's calculate first our partial derivatives. The derivative of phi with respect to r is cosine theta, sine theta, and negative 2r. The derivative of phi with respect to theta is going to be negative r sine theta, r cosine theta, and 0. So I've calculated d phi dr and d phi d theta. Now let's take the cross product. So to take the cross product, I'll write my I, j, and k up here, and we'll take the determinant of this matrix. So d phi dr crossed with d phi d theta is going to be I times 0 minus a negative, so plus 2r squared cosine theta, comma, minus j times 0 minus 2r squared sine theta plus k times r cosine squared theta minus a negative r sine theta, sine squared theta. Putting this into our familiar vector notation, that's going to be 2r squared cosine theta, comma, multiplying the negatives, 2r squared sine theta. And since sine squared plus cosine squared is 1, my last component is just r. So I no longer need my parameterization. And let me just make a note over here that r is going to go from 0 to root 3, and theta is going from 0 to 2 pi. I'll save that for later. So now I want to take the magnitude of d phi dr crossed with d phi d theta. Something that will save a little bit of work is to factor out the r that I have in common. And then take the magnitude of that. So the magnitude of d phi dr crossed with d phi d theta is equal to, remember when you take the magnitude of a scalar times a vector, it's the absolute value of the scalar times the magnitude of the vector. So it'll be the absolute value of r times the square root of 4r squared cosine squared theta plus 4r squared sine squared theta plus 1, which is the absolute value of r. 4r squared cosine squared theta plus 4r squared sine squared theta is just 4r squared. And then plus 1. So ds is equal to the magnitude of d phi dr crossed with d phi d theta, which is the absolute value of r times the square root of 4r squared plus 1 times dr d theta. Notice, though, that since r is going from 0 to the square root of 3, r is positive, so I don't really need the absolute values here. And that's the end of step 2. Step 2 is to calculate the surface area element, ds. Step 3 is to set up the integral and evaluate it. So remember, surface area is the double integral over the region R in the r theta plane this time of ds. We calculated ds to be r times the square root of 4r squared plus 1 dr d theta. And earlier, we saw that the bounds on r are from 0 to square root of 3, and the bounds on theta are from 0 to 2 pi. Well, notice that there are no thetas involved, so I can break this up as the product of two integrals. I can write this as the integral from 0 to 2 pi of just 1 d theta times the integral from 0 to square root of 3 of r square root of r squared, 4r squared plus 1. Now, I am going to do this using a u substitution, so let me rearrange this just a little bit. Let me write this as 4r squared plus 1 to the 1/2 power times r dr. Of course, this first integral just gives us 2 pi. That's the easy part. Now let's work on the u substitution for this part. If I set u equal to 4r squared plus 1, then du is 8r dr. I have an r dr, so I can multiply and divide by 8. So inside, I get u to the 1/2 du. But I also need to adjust my bounds. Notice that when r is equal to 0, if I plug in r equals 0, I get u equals 1. And if r is the square root of 3, if I take the square root of 3 and plug in, I get 4 times 3 plus 1, which is 13. So my bounds for u are from 1 to 13. So in front, 2 pi over 8 is the same as pi over 4. The antiderivative of u to the half is u to the 3/2 times 2/3. And I'll be taking that from u equals 1 to u equals 13. Simplifying here, I get pi over 6. And if I plug in my two endpoints and subtract, I get 13 to the 3/2 power, which is 13 root 13, minus 1 to the 3/2 power, which is 1. So the surface area of this paraboloid, or this piece of the paraboloid, is pi over 6 times 13 root 13 minus 1.